Hi everybody, this is James Tompkins and welcome to another Understanding Finance Nugget. And what I'm going to do right now is what I would consider a challenging time value of money problem. In fact, if you can do this problem, in my opinion, you can do cartwheels with time value of money. There's nothing you wouldn't be able to do. This would prove you have an in-depth understanding. So some prerequisite nuggets necessary to understand this. Well, two rates commonly used in time value of money equations, or deriving the only single cash flow formula that exists, and deriving the present value of an annuity. And of course, you could always watch the two lectures also, the single cash flow lecture and the multiple cash flow lecture, which has all this together in chronological order. Anyway, this is an example of what would be, I would say, a challenging time value money problem. Like I said, if you could do this, wow. And what I've done is I put the answer down there, $449, that's without rounding. And you try it on your own. And if you can do it, then great. You obviously don't need to look at those other two lectures or any of these nuggets and so on and so forth, and can just move on. Now, when I do this in class, we actually make up a real-life example. Usually there's somebody in my class who has a young child, and so I've made up the names here. So let's say Jane, she's in my class, and she's got a daughter called Sarah, and let's say Sarah's 2 years old, and she's going to start college in 16 years. And let's say she's going to be on the semester system, and we're just going to assume that tuition for college is due twice a year, payable, I'm guessing, in advance. Now, imagine today the cost for college is, say, $20,000. That's for every 6 months. And let's say she tells me, well, we want to assume 3% inflation. So if you do sort of a back-of-the-envelope calculation, 20,000 at 3% in 16 years, this isn't exact. We're just kind of figuring this out roughly. About $32,000 every 6 months. Then I usually say, well, hey, is Sarah wrapped around your little finger and she can take 8 years or 6 years to do college, or does she have to get it done in 4 years? And well, most parents want their kids to get out in 4 years. I know I want my kids to get out in 4 years. And let's say that Jane has a husband called George, and they've already saved up $14,000 at this point. Now, of course, they're going to have to make an assumption as they save their money, the rate at which it'll earn interest or returns or whatever. And so let's just say, you know what? Let's assume a rate of 8% compounded quarterly. So here's the question. Beginning today, so Jane goes home to George, tonight, and says, hey, honey, we need to start saving for college right now for Sarah today. And let's say that they want to finish saving 1 month prior to Sarah starting college. Okay, so they don't want to have to keep saving while Sarah is still in college. And the question is, if we assume an equal cash flow, or so maybe the answer is $100 every month. If we assume an equal amount, what is that amount going to be? So there's a bunch of verbiage, right? I mean, you could go back to the second slide or third slide, whatever it was where this problem originally was, and there was a whole paragraph of verbiage. Now, what's the first thing that you're going to do before you do any finance whatsoever? Well, you're going to take a stand on the interpretation of the problem. And what does that mean? That means drawing a cash flow timeline diagram. So let's begin with what they actually have to put aside. Okay, so imagine C represents the cash flow amount that they put aside. And we said that Jane and George were going to start saving. They're going to procrastinate. They're going to wait a month before they start. They're going to start right now. They're starting right now, right? So if time 0 is today, then right now this represents the first cash flow. And what do these periods have to be? Well, how often are they saving? Every month, right? So the periods are monthly, and so they're beginning today, and And we said that Sarah was going to begin college 16 years from today. And we said that the parents, Jane and George, they wanted to finish one month, the last savings, they want to be 1 month before Sarah starts college. So when is the last month of savings? Well, we got 16 years. How many months in a year? 12 months in a year. So 16 times 12, so 192 months until Sarah goes to college. And so if this is t equals 192 months, then the last savings will be at t equals 191. So any other cash flows that are relevant to their savings? Well, do they already have some money saved up? They do, right? If you recall, that was $14,000. So where would I put the $14,000 on this cash flow timeline diagram? Well, if they have it today, is it 14,000 at time 0? It is, right? So it'd be 14,000 at time 0. So those represent all the savings, if you will, cash flows. Now what about the payments? Okay, so if this is today, and if 0 prime is when Sarah starts college, so 192 months from today, then we already figured out, or we've assumed. Jane has asked me to assume, hey, let's assume $32,000 payable in advance every 6 months, in which case how long do these periods have to be? Well, they're 6-month periods, right? And how many of these payments do we have? Well, they said they would fund 4 years, correct? And they're 6-month periods. So how many payments is that in total? That's 8, right? So there's 8 of these 32,000s. So when is the last payment? Well, that'd be times 7, right? And you're going, huh? There's 8 payments. Well, I know, but the first payment begins at 0 prime, right? So you want to see a trick? Check this out, okay? If I'm beginning with 0, 0 prime, 1, 2, 3, 4, 5, 6, 7. Look, I ended with the number 7, but how many fingers am I holding up? 8, right? So in any case, point is there's 8 of these 32,000s. So here's my question. We have it all together. Here are the savings. Here are the outflows, what the savings will support. So does there exist a number that I can put here, the amount that Jane and George are going to put aside every month, given the 8% compounded quarterly that we're assuming, that would make me indifferent between all of these cash flows here and all of those cash flows out there? Does that conceptually exist? It does, right? And that's what we're going to solve for. So how do you do this? Well, basically, the approach is, step 1 is we're going to take all of these guys right here and crush them into one single number at one single time period. And then we're going to take all of these guys right here and crush them into one single number at the same time period. And if they're at the same time period, like let's say all of this is equivalent to something at time 0, and all of this is equal to something times c, because it's a function of c at time 0, as long as they're in the same time period, can I set them equal to each other? I can, right? But if they were in different time periods, could I set them equal to each other? No, it'd be like setting euros equal to yen, right? You can't do that. So they have to be in the same time period. Now, before we get into all the numbers, just to illustrate what I'm talking about, before we get into all these real numbers, suppose the left-hand side, so all my savings came to, we already said it'd be a function of c, right? Say 1,000 c at time 0. And say the right-hand side, when I took all of those numbers and brought them all back to time 0, say they came to, say, $1 million. And again, if they're both in the same time period, can I set them equal to each other? I can, right? So in that example, we'd have 1,000C at time 0, say, equals $1 million. And at this point, it's just a question of solving for C. So divide both sides by 1,000, and I get, all right, well, C, a million over 1,000, C comes to $1,000. So that's the big picture of this problem, and I just thought it'd be worth getting that across before we get into the real numbers. So I'm a time 0 kind of a guy, okay? I don't know why. Maybe I was just born that way, but I'm a time 0 kind of a guy, so I'm going to solve for everything in time 0. You might solve for everything at graduation. As long as both sides are in the same time period, you'll get the exact same answer. And the best way to prove that to yourself is maybe to try it both ways. All right, so here I have the savings. We'll start with that. Doesn't really matter what side you start with. Now these are monthly periods. So I better be working with what kind of an effective rate? I better be working with an effective monthly rate, right? Which means what? Amount of interest made from $1 after 1 month. Brilliant. Okay. Now we're told a rate of 8% compounded quarterly. Okay. So question, is it a single cash flow to figure out the equivalent effective monthly rate? It is, right? Now you should try that on your own and see, if you can get that. It's single cash flow principles. I mean, I'll go ahead and do that, but you should, if I were you, I'd pause it and see if you can get this on your own. So 8% compounded quarterly, what's the equivalent effective monthly rate? Now this 8% compounded quarterly, what kind of rate is that? That's a nominal or stated or advertised rate by definition, right? Because unless something specifically tells you, hey, this is an effective rate, what do you have to assume? You have to assume it's a nominal or stated advertised rate. And also, by definition, what is the only first step that I can take with that 8%? I mean, there's absolutely nothing else that I can do as a first step. By definition, is to divide it by 4. Why? Because by convention, this 8% is an annual number. There's 4 quarters in a year. So 8 divided by 4 gives me 2%. And now, by definition, I have my effective quarterly rate. So by definition, what does that mean? That $1 will grow into how much after how long? Well, basically, $1 is going to grow into $1.02 after 1 quarter. So the question, however, says, well, what is the effective 1-month rate? All right, well, what is that again? I forgot. Amount of interest made from $1 after 1 month. So question, does there exist an effective monthly rate such that $1 will grow into $1.02 after 3 months or 1 quarter? There does, right? I mean, that conceptually exists. So if I had monthly compounded, there exists a rate at which $1 would grow into $1.02. Now, is that a single cash flow problem? Sure. Using the only single cash flow formula exists, this guy right here, which if you looked at the deriving this formula nugget, you already know that. You should not be memorizing that. Okay? Using the only single cash flow formula exists, what would I put in for my future value? Well, the future value is the later value, right? So what's the later value in this problem? $1.02. What's the present value or the earlier value? $1, right? What's my R? Well, that's what we're trying to figure out, right? We're trying to figure out the effective monthly rate. And if this is going to be an effective monthly rate right there, then the T is going to be in what kind of units? Months, right? So how many months am I bringing this dollar forward? 3, right? So what number do I put there? 3. So if I put in those numbers, $2 equals 1 times 1 plus RM cubed, and I solve for RM. How would I do that? Well, I take the cube root on each side, so 1.02 to the third, and this to the 3 over 3, so that gets rid of the 3. And I subtract 1, and I get 0.00662. So that's my effective monthly rate. So now going back to the problem, here are all my savings, right? These are monthly periods, so I'm working with the correct effective monthly rate. So all of the C's, is that an annuity? It is, right? So can I apply my annuity formula? Sure. So if you look at the annuity formula, again, this is something that we derived, then what is my C? That's what I'm trying to figure out. These are monthly periods, so what have I got here? An effective monthly rate. And how many of these guys are there? Well, I begin with 0, and I end with 191. So how many of these C's are there? 192, right? You know, another way to think about that is, if I didn't have this first C at time 0, then how many of these guys would I have? I'd have 191, right? So 191 plus this one at time 0, so 192 is 2. So given that there are 192 of these cash flows, then what number would I put here? Well, you can see it. It'd be the 192. So here's my question. And by the way, if that wasn't totally clear, then I strongly recommend you go back and look at the derivation of an annuity, and then you'd understand the application of this stuff. Also relevant, by the way, to that is, all right, if you understand the application of this, then for what time period is this true? In other words, if I had a C, I'd have a single number at a single time period, right? Well, for what time period is this true? Well, when you apply an annuity problem, an annuity formula, then is the solution at the same time period as the C or one period earlier? It's one period earlier, right? So if the first C is at time 0, then all of this is going to be at what time? T equals minus 1 month, or 1 month ago. So basically, all of these guys right here is the equivalent to this much at time minus 1. But I want it at time 0. I don't want it at time minus 1. I want to move it forward 1 month. Well, was that a single cash flow problem? It is, right? Would I multiply it or divide it by something? I'd multiply it by something. What would I multiply it by? Well, 1 plus the effective monthly rate. If I said, hey, $100, 10%, I need to move that $100 forward 10%. What would the $100, what does it grow into? You tell me 110, right? Well, that's just taking the 100 and multiplying it by 1 plus 0.1. So we're doing the same thing here. We're taking this and we're multiplying it by 1 plus the relevant effective rate. In this example, an effective monthly rate. So what we have is, now we've got all of this for the C's is what it's equal to at time 0. So question for you. Are there any other relevant cash flows? Anything else? We've accounted for all the C's. Is there anything else going on? Well, there's the 14,000, right? Now, is that already at time 0? It is, right? So can I just add that to the formula I had before? I can, right? Because can I add a time 0 value to a time 0 value? Sure. So here we have all of this. This is what the C's are worth at time 0. I add my time 0 value, and I've achieved the goal, at least on the left-hand side, of crushing all of these guys into one single number at one single time period. So what do we do now? Well, now we're going to move to the right-hand side and do the same thing over here, and I'm going to put it in what time period? Time 0, right? You have to put both sides equal to in the same time period. So let's move to this side. So these are 6-month periods, so I better be working with what kind of an effective rate? Effective 6-month rate, right? So again, we're told 8% compounded quarterly. Is it a single cash flow problem to figure out what the equivalent effective 6-month rate is? It is, right? Now again, I would encourage you to try this on your own. And there's the answer, 4.04%. So, again, I'll go over it. But if I were you, I'd pause and try it on your own, and then check what I've got. So let's go ahead and figure it out right now. So a bank pays 8% compounded quarterly. What is the equivalent 6-month effective rate? Now again, what is the only first step that I can take with that 8%? Well, by definition, divide it by 4, right? Why? Because this is a nominal or stated advertised rate. By convention, the 8% is annual. And how many quarters in a year? 4, right? Brilliant. So just by definition, I divide by 4, and now I have my effective quarterly rate. So what does that mean? What does it mean that the effective quarterly rate is 0.02? That $1 grows into how much after how long? Grows into $1.02 after 1 quarter. But we want the effective 6-month rate. Well, what's the effective 6-month rate? Well, how much $1 grows into after how long? After 6 months. Well, we know that $1 after 1 quarter grows into $1.02, right? So is it a single cash flow problem to figure out what it grows into after 2 quarters or 6 months? It is, right? It's just a future value problem. So using the only single cash flow formula that exists, here it is right there, what do I put in for future value? Well, that's what I'm trying to figure out, right? What do I put in for present value? Well, I can either put in this dollar and move it forward 2 periods, or I guess I could put in $1.02 and move it forward 1 period. Either way, you'd still get the same answer. So I'll just begin with the dollar. And what do I put in for R? Well, these are quarterly periods, so I better be working with what kind of a rate here? An effective quarterly rate, right? And if I'm beginning with $1, then what do I put in for my T? 2, right? Because I'm moving the dollar forward 2 quarterly periods. So if we put that together, then the dollar would grow into $1.0404. And so how much of that is interest? Well, 0.0404, right? So therefore, what is the effective 6-month rate? i.e., the amount of interest after 6 months. Well, subtract the original dollar. So 0.0404 is my effective 6-month rate. So now that we have that, these are 6-month periods. I've got my effective 6-month rate. Is this an annuity right here, all those 32,000s? It is, right? So can I apply my annuity formula? Sure. So if I pop in my annuity formula, again, 32,000 is my C. These are 6-month periods, so I'm working with an effective 6-month rate. How many of these 32,000 do I have? I have 8 of them, right? So I'm putting an 8 right here to represent the number of cash flows. And I'd get about 215,000. So here's my question. And if you can get this question right, then I would suggest to you that you have a pretty good understanding of this annuity formula. So here's the question. For what time period, this 215,000, for what time period is it true? Well, when you apply an annuity formula, then is the solution at the same time period as the first cash flow, in this example 32,000, or is it 1 period earlier? Well, it's one period earlier, right? So what is one period earlier than 192? Well, if you said 191, sorry, you'd be wrong. Think about why. Well, how long are these time periods? 6-month time periods, right? So you're working with an annuity where we're using 6-month time periods, an effective 6-month rate. So yeah, it's still one time period earlier than this 192, but it's 1 6-month time period earlier. And so what is 6 months earlier than 192? Well, it's a time period 186 months from today. So basically, all of this is equivalent to about $215,000 at t equals 186, or time 186 months from today. So if we look at what that looks like, okay, next question is, so here are all the 32,000s. This is when Sarah starts college and mom and dad make these payments, and that's all mathematically exactly identically equivalent to this much at 186. But do we want this time, this 215 at time period 186? We don't, right? What time period do we want it? Well, we want to bring it back to time 0. Why? Because if you recall, we're going to set the left-hand side equal to the right-hand side, but they both have to be in the same time period. And as I mentioned, what kind of a guy am I? I'm a time 0 kind of a guy, okay? And so is it a single cash flow problem to bring the 215,000 back 186 monthly periods? It is, right? Would I multiply it by something or divide it by something? Divide, right? And if I'm bringing it back 186 monthly periods, I better be working with what kind of an effective rate? Well, an effective monthly rate. So bringing this back 186 monthly periods using the effective monthly rate is equivalent to about 63,000 at time 0. So basically, if we put it all together, here's the 63,000 at time 0. So that represents all of these guys. All of this represents all of those guys, right? All the C's and the 14,000. And at this point, it's algebra, right? We have one equation, one unknown, and so we can solve for C. And if you did that using the numbers you see there, you'd get $452. But if you get a slightly different answer, it's because I've been rounding. And the answer without rounding is about $449. So again, let me just make a comment. If you were either able to do this before I even went through it, wow, that's amazing. I mean, that tells me you have a solid understanding, not memorization, understanding of this stuff. And if you understand what we just went through, then again, you have a solid understanding of this stuff. You're not just have the level of understanding where you go, all right, well, I know what buttons to push on what calculators or what numbers go where. You could be the programmer, if you will. And so on that note, I would suggest that you have an in-depth understanding of this stuff, and congratulations. And if you do want to see another challenging time value money problem, there's another nugget that's out there, another challenging problem. Very different from this, but not quite as challenging as this, I would say, but still pretty challenging. In any case, this is James Tompkins, and I hope this was a good learning experience. And I hope to see you in my lectures or nuggets. Take care. Bye.